Hello, everyone. So this is Teacher Kimi, your trans teacher. I hope so that everybody's doing fine. Here we go again for another exciting discussion of our physical science. But before that, just spare me a little bit of your time because I'm gonna prepare my food for a while. I'm still hungry. And sit back, relax, and help me in preparing my food.
Now, cooking the adobo makes it so easy and so yummy. Do you wonder why some of those chicken are chewy and tender? Yes, maybe some of those ingredients serves as catalyst in the reaction. What is catalyst? Catalyst fastens the rate of reaction in a lower temperature, in a lower activation energy. So what is activation energy? So let us try to discuss what is activation energy.
Activation energy. Activation energy is the minimum energy required for a chemical reaction to occur. According to collision theory, two conditions are necessary for a reaction to occur. 1. Particles must collide with correct orientation, and 2. Particles should have sufficient energy to break existing bonds and form new ones. The minimum energy that will allow this reaction to happen is known as the activation energy. At the activation energy point, the colliding molecules have formed a transition state in which old bonds are partially broken and new bonds are partially formed. The transition state is present at the top of an energy hill. Reaction can either proceed to form new bonds and convert into products, or it can reform the old bonds and return back to the reactants. Therefore, activation energy is also known as the potential energy barrier that separates reactants from products. For example, in this reaction, when OH- and CH3Br react to form CH3OH and Br-, the old CH3Br bond must break and a new OH-CH3 bond must form. The reaction coordinate diagram for this reaction shows that the reactant molecules OH- and CH3Br and the product molecules CH3OH and Br- are stable, and their stability corresponds to the low levels of potential energy. However, during the transition between reactants and the products, there is a high energy, unstable state known as the activated complex. From the potential energy curve, we can easily derive that the activation energy for any reaction is equal to the difference between energy of activated complex and the reactants. Effect of catalysts on activation energy. A catalyst is a substance that speeds up the rate of a chemical reaction without being used up in the reaction. Catalysts follow a different pathway which has lower activation energy than the one followed by the uncatalyst reaction. As a result, a greater proportion of reactant particles have enough energy to complete the react. Effect of temperature on activation energy. At low temperatures, only a small fraction of the colliding molecules will have enough energy to overcome the activation energy barrier, and therefore the reaction will proceed slowly. However, at higher temperatures, more molecules have the minimum energy needed to react, and it will speed up the reaction. The dependence of the rate of reaction on temperature can be observed in our homes as bread rises faster in warm environment because the chemical reactions happening inside the yeast increase at higher temperatures. In 1899, a Swedish chemist, Svante Arrhenius, combined the concepts of activation energy and the Boltzmann distribution law into one of the most important relationships in physical chemistry. Arrhenius proposed an equation to determine activation energy of a reaction. Let's solve an example to calculate activation energy of.
Now let's proceed with the computation of the activation energy, wherein we have a general formula for the activation energy, wherein K is equal to A, E raised to negative E, A all over R and T, where K denotes as the constant of the reaction. Then we have the big letter A, which denotes the pre-exponential factor, and then the E is the base for the natural logarithm, and the big letter E denotes the activation energy of the chemical reaction. And then the big letter R, it is the gas constant, and then we have T denotes the temperature in Kelvin scale. So getting the logarithm of the Joule formula for the activation of energy, we have natural logarithm K is equal to negative E A all over R, quantity 1 over temperature plus the natural logarithm for the pre-exponential factor. And then we have also L, the natural logarithm of K is equal to E all over A all over the gas constant plus the natural logarithm for pre-exponential factor 2. That is why we will arrive now to the formula. Natural logarithm K is equal to negative E all over the gas constant and times temperature plus the natural logarithm A 3. And then deriving now, we will have the natural logarithm. So comparison. So the natural logarithm for K1, K2 all over K1 is equal to EA all over RT times the quantity 1 over T2 minus 1 all over T1. Then to further derive the formula in finding the activation energy in chemical reaction, we can have the activation energy is equal to the gas constant times temperature 1 times temperature 2 all over the quantity temperature 1 minus temperature 2 quantity times the natural logarithm of K1 all over K2. So that will be the formula for the activation of energy. So example, we have this one. So a second order reaction was observed. The reaction rate of the constant at 3 degrees Celsius was found to be 8.9 times 10 raised to negative 3 liters per mole and 7.1 times 10 raised to negative 2 liters per mole at 35 degrees Celsius. What is the activation energy of this reaction? So the general formula for this one, we have the natural logarithm for the comparison of the K2 all over K1, which is the rate constant, then is equal to the activation energy all over the gas constant times quantity 1 all over T1 minus 1 all over T2. So just what I have mentioned a while ago, E denotes as the activation energy for the reaction, which is in joule per mole. And then the R is the ideal gas constant, which is equivalent to 8.31 joule per Kelvin mole. And then for T1 and T2, that is the absolute temperature in Kelvin scale. Then K1 and K2 is a reaction constant at temperature 1 and 2. So let's try to solve the problem. So if we try to solve the problem, we have step 1. So let's try to transform first the temperature into Kelvin scale. So for T1, which is 3 degrees Celsius plus 273.15, so temperature 1 will be 276.15 Kelvin. And then for temperature 2, that is 35 plus 273.15. So the equivalent Kelvin is 308.15 Kelvin. Now let's proceed with step 2. So let's try to find for the activation energy. So using the formula, natural logarithm ratio of K2 all over K1 is equivalent to the activation energy all over the gas constant times 1 all over temperature 1 minus 1 all over temperature 2. Next thing, we will now have substitution of the given. So we have 7.1 times 10 raised to negative 2 and 8.9 times 10 raised to negative 3. That is the rate constant of the reaction. Times the activation energy all over the gas constant, which is 8.3145 joule per Kelvin mole, times the temperature in Kelvin scales. So that would be temperature 1 is 276.15 minus 1 all over 308.15 Kelvin. So activation energy, so using now the transposition method, we could have the value for the activation energy. So we have 2.077 all over 4.52 times 10 raised to negative 15 mole per joule. That would be equivalent to 4.59 times 10 raised to 4 joule per mole. Or we can have other answers in kilojoules. So we can have 4.59 kilojoules per mole. So we have next problem. For problem number 2. So for problem number 2, we will use the general formula for the activation energy. So the rate constant for the first order decomposition of a certain reaction is described by the equation log of K, or natural logarithm of K, is equal to 14.34 minus 1.25 times 10 raised to 4 Kelvin, or K, or for the reaction rate rather, then all over the temperature. So the question is, what is the energy of activation for the reaction? At what temperature will its half-life period be in 256 minutes? So you can see there in the problem that the general formula is given. So we will try to substitute the formula given with the derived formula we have earlier. So again, the formula for the activation energy, we have the natural logarithm of K is equal to natural logarithm of A minus the activation of energy all over the gas constant times temperature. So log of K is equal to, or the natural logarithm of K is equal to 14.34 times 10 raised to 4 reaction rate all over temperature. So we have 1.25 times 10 raised to 4 is equal to activation energy times the constant 2.303 RT. That is the reaction rate. So multiplying the two values, we will have now the activation energy is equal to 2.39.33 kilojoules per mole. If you consider in the problem, we have the 2.303. So that is the conversion factor for the natural log to lag of 10 for the reaction rate. So let's proceed now for the question for the half-life. So again, using the formula, K is equal to the natural logarithm of 2 all over the temperature half-life. So sub half-life is equal to 0.693 all over 256 times 60. So that's equivalent to 1 hour. Therefore, the half-life would be 4.5. So using the formula given the problems, you have log of K or the natural logarithm of K is equal to 14.34 times 2.5 times 4, the reaction rate all over T. So we will try to substitute it. So we have log of K is equal to 14.34, which is given in the problem, times 1.25 raised to 4 reaction rate all over time. So all the values that we have derived from the computation earlier, we will try to substitute it now. So we have 1.25 times 10 raised to 4. That is the reaction rate. We have 4.34 minus log of 4.5 times 10 raised to negative 5. So we have 1.25 transposition method. So we will have the temperature would be 669 Kelvin. So that's all for the day. Thank you very much for listening in our activation energy topic. Thank you very much and see you soon. Bye-bye. See you soon. Bye-bye.